Look at this machine for a moment. It weighs over 14,000 tons. Its bucket alone can hold more than 100 cubic meters of material in a single scoop, and when it swings that arm sideways, extending dozens of meters out from its body, nothing happens. It doesn't lean. It doesn't shift. It doesn't fall. That shouldn't be possible. And if you've never stopped to ask why, you're about to understand something most people never think about. Here's what makes this strange. When you extend a heavy object away from a fixed point, the torque, the rotational force trying to tip that object over, increases with distance. It's basic physics. A child can tip a large box if they push at the far edge rather than the center. So, when a machine with a 500-ton boom extends outward and scoops up 80 tons of rock, the tipping force acting on its base becomes enormous. You'd expect the machine to rotate, to lose its footing, to collapse sideways. It doesn't, and the reason why involves a system most people never realize exists. Let's establish the scale we're dealing with. The Bagger 293, currently the largest land vehicle ever built, operates in the lignite mines of Germany. Its total operating weight exceeds 14,200 metric tons. That's heavier than the Eiffel Tower. Its excavation wheel alone measures 21.6 meters in diameter. The machine stretches 220 meters in length and stands 96 meters tall. It moves on crawler tracks, not wheels, each track unit weighing hundreds of tons on its own. The boom arm extends far beyond the machine's footprint. At full reach, the bucket can swing out over ground the machine itself is not standing on. During operation, it removes up to 240,000 cubic meters of earth per day. And throughout all of this, the machine remains stable, precisely stable. Smaller excavators face the same physics problem, just at a different scale. A 90-ton hydraulic excavator, reaching out to dig at the far edge of its range, is generating tipping forces. Without compensation, these forces would pull it forward. So, how does any of this work? The common assumption is that excavators don't tip because they're heavy enough, that their own mass is sufficient to hold them in place. This is wrong. Weight alone does not prevent tipping. What matters is where that weight is located relative to the tipping axis. A machine can be extremely heavy and still tip if the center of mass moves outside the support boundary. Weight distribution is the actual variable, not total weight. The second common assumption is that the crawler tracks solve everything, that the wide base provides all the stability needed. This is also incomplete. Track width does extend the tipping boundary, but it doesn't eliminate the problem. It just shifts the threshold. The tipping physics still exist. They just require more reach to trigger. Real excavator stability is the result of intentional design decisions built into the machine from the start. Decisions that actively manage where the center of gravity sits at every point during operation. There are three fundamental mechanisms at work. They operate simultaneously, and each addresses a different part of the stability problem. The first is counterweight. At the rear of the upper structure, the part that rotates, there is a large mass of dense material, cast iron, steel plates. In large machines, this counterweight can reach 10 to 15% of the machine's total operating weight. Its purpose is direct. It creates a moment, a rotational force, in the opposite direction of the load. When the boom extends forward and picks up a heavy load, the front of the machine experiences a forward tipping moment. The counterweight at the rear simultaneously generates a rearward moment. If these two moments are balanced, the machine remains stable. If the load is too large, the forward moment exceeds what the counterweight can resist, and the machine becomes unstable. But counterweights alone don't solve the problem. The second mechanism is geometry control. The shape of the boom, the arm, and the bucket determine how far the load's center of mass is displaced. Excavators are designed so that their full working envelope is calculated against the machine's rated capacity. Operators are trained to work within specific load charts that define the maximum load at a given radius and height. Exceeding those numbers places the machine in a zone where the margin has been eliminated. The third mechanism is the support footprint. This is the area defined by the machine's tracks or outriggers. For the tipping axis to matter, there must be a defined edge, a boundary beyond which the load pulls the machine over. Wide crawler tracks extend that boundary outward. Outriggers on smaller machines do the same. The interaction between these three systems is what actually keeps the machine upright. None of them works alone. To understand why this works, we need to be precise. Stability is not a binary state. It exists on a continuum defined by the relationship between two things, the tipping moment and the restoring moment. The tipping moment is the product of the load multiplied by the horizontal distance between that load and the tipping edge. If a machine is lifting 50 tons at 10 meters from its axis, the tipping moment is 500 ton-meters. The restoring moment is the machine's own weight multiplied by the distance from its center of gravity to the tipping axis. If the machine weighs 300 tons and its center of gravity is 3 meters back, the restoring moment is 900 ton-meters. In this case, the restoring moment exceeds the tipping moment. The machine is stable. There is a margin. If the load increases or if the boom extends further, the tipping moment grows. When the tipping moment equals the restoring moment, the machine reaches what engineers call the tipping point. Not metaphorically, but literally. Ground reaction at the rear tracks drops to zero. The machine is balanced exactly on its tipping edge. Beyond that point, the machine begins to rotate, and once it starts rotating, it accelerates. There is no recovery. This is why counterweight placement is so precise. Every kilogram of counterweight added at the rear increases the restoring moment, but it also increases total machine weight, which affects mobility, ground pressure, and transport requirements. It's an engineering optimization, not a simple addition. Modern large excavators use load monitoring systems that measure forces at the boom base. Some include automatic alarms or load limiters that prevent the operator from exceeding the machine's stability envelope. These systems don't replace the physics. They make the physics visible and manageable. In open-pit mining, where machines like the Bagger 293 operate, the ground itself is the first variable. Soft, overburden; wet clay; compacted gravel. Each surface type changes how the machine's weight is distributed across its tracks. Uneven ground shifts the effective center of gravity. A machine that was perfectly stable on level ground can approach instability on a slope. That's why mining-scale excavators operate on prepared benches, leveled platforms cut into the mine face. The stability calculations assume a specific ground angle. Deviation from that angle is deviation from the design envelope. On construction sites, hydraulic excavators face the same physics in a more dynamic environment. They work on uneven terrain, near edges. Outriggers, extendable stabilizing legs, are used to artificially extend the support footprint when the machine needs to lift heavy loads. When outriggers are deployed, the tipping axis shifts from the track edge to the outrigger pad. This can nearly double the effective stability base. Cranes, which are essentially specialized lifting machines with the same stability problem, use this principle even more explicitly. Mobile cranes carry charts that specify the maximum load at every radius and every ground configuration. Outrigger pad size, outrigger extension length, ground bearing capacity, all of it is calculated before the lift begins. A crane operator ignoring those charts is not taking a risk. They are operating a machine outside its design envelope. These systems work within their design parameters. Outside those parameters, they fail. And they fail in ways that can be catastrophic. The most common failure mode for large excavators is ground collapse. The machine's load calculations assume a specific ground-bearing capacity. If the soil under the tracks gives way, suddenly, as can happen in mining environments near blast zones, or water-saturated ground, the effective support footprint changes in milliseconds. A machine that was stable before becomes unstable the moment one track sinks deeper than the other. For smaller excavators, The most common tipping incident occurs during travel on slopes. When a machine travels across a slope, perpendicular to the fall line, the center of gravity shifts laterally. If the slope angle exceeds the machine's rated side slope capacity, the machine tips. This happens more often than most people realize, and it happens fast. Overloading is the other common failure mode. Load charts are not conservative estimates. They are the actual calculated limits for the machine's stability envelope. Exceeding those limits while lifting reduces the stability margin to 0 or below. If an operator estimates the load incorrectly, which is easy to do when lifting buried material of unknown density, the machine can tip without warning. At the scale of machines like the Bagger 293, the consequences of any instability are severe. A machine of that mass cannot be quickly stopped. If the tipping moment begins to exceed the restoring moment, there is no recovery. The machine goes over. The engineering challenge isn't just to make the machine stable, it's to make it impossible to accidentally operate it outside its stable range. So why doesn't the world's largest excavator just tip over? Not because it's too heavy to move, not because the tracks are wide enough to hold anything, and not because the engineers got lucky with the design. It stays upright because of a precise, calculated balance between three things: the tipping moment generated by every load at every position, the restoring moment generated by the machine's own weight and counterweight, and the support boundary defined by the tracks or outriggers. These three factors are in constant relationship with each other during every second of operation. When the load increases, the geometry adjusts. When the radius changes, the operator works within a defined envelope. When the ground changes, the machine is repositioned. Stability isn't a property the machine has. It's a state the machine is constantly being kept in, by design, by procedure, and by the physics that can't be ignored. If you found this interesting, there's a related question worth thinking about. When a machine like this reaches its tipping point, when the restoring moment drops to 0 and the machine is perfectly balanced on one edge, what happens to the ground underneath? The forces transferred into the soil at that moment are concentrated at a single line. The ground pressure at the tipping edge goes to extraordinary levels. Whether the ground holds or fails at that moment changes everything. I've covered how machines interact with the ground under extreme loading in another video. The physics of soil-bearing capacity and how it's calculated before any large machine moves into position. That's a topic that connects directly to everything.